we will continue the afternoon session of the day. The first talk is given by Hal Tasaki. He already got his first talk yesterday morning, and he will now give his second talk on spontaneous symmetry breaking and angular formation in Chicago post Einstein and condensates. Let's welcome the speaker.
Thank you. So since this is my second talk, I decided to talk about something totally different. And so the style of the slide is also different. Less colors. And this will be, I think, the least fashionable talk in the conference. Nothing related to something fashionable, fancy. So this is about more fundamental thing, basic thing about quantum many-body system related to long-range order. And this is actually based on my old collaboration with my colleague Toru Koma, and I found the date, it was 93, it's a long time ago, and I was as young as some of you, like years ago. but very recently I made some improvement of this thing, so today I'm going to talk about the old thing with improvement and some application to BEC. And oh, by the way, this is how you spell Koma. And so by this, you see that you know where his ancestor came from. Also, the pronunciation is somehow went wrong for this. Ko is, I think. But anyway, this is and okay. So before going into quantum system, I like to start from a warm-up about talking about something everybody knows. That's a classicalism. And so this is the definition everybody knows. But anyway, okay, throughout the talk, lambda denote the d-dimensional hypercubic lattice with size L. And I denote by d the number of sides L to the d. And d is always greater than or equal to 2. And now I define Ising model. And as usual, for each side x, we define sigma x, which takes plus or minus 1, and Hamiltonian is this. You sum over nearest neighbor pairs. Probably you are counting twice, but I don't care. This is Ising Hamiltonian, and you define corresponding thermal expectation like this. Okay, this is very standard. And it is very well known that this model exhibits from magnetic phase transition at finite temperature. And to see this, it's convenient to introduce order parameter. And in this case, order parameter is nothing but the total magnetization. And then it is very well known that there is some finite BEC, and this is rigorously proved. But this was not proved fully when I was a student, but it's now totally proved thanks to the mathematical physicists. And we know that there is some finite BEC, and if your beta is below BEC, that means you are at high temperature, then two-point function decays exponentially with finite sign. And in this case, if you look at the expectation value of O squared, and this is a double sum, and if you first fix x and sum over y converges, you get a finite quantity. So this becomes, and you can just sum over x to get v. So this will become v times some finite quantity. So this is over v. That's high temperature, and if you go to low temperature, then you know that now this two-point correlation function does not decay, no matter how far they are separated. And it converges to a non-vanishing quantity, positive quantity that I denote by m star squared. And now in this case, if you consider O squared, expectation value of O squared, of course it becomes m squared times v squared. Okay, so this is long-range ordering. They are ordering far away. But by symmetry, since I'm not imposing external field, by symmetry you find that the expectation value of O itself is vanishing. So there's no symmetry breaking in this situation. So if you look at the low temperature phase with this expectation value without magnetic field, you see that O squared is proportional to V squared, but the expectation value of O is 0. And this means that if you look at the variance of O, this is of order V squared. And this means that this quantity O exhibits a huge fluctuation of order V. And of course, this is a macroscopic quantity of order V. Its fluctuation should be less than a smaller order of V, usually square root V or something like that. But this is very weird. It exhibits a huge fluctuation proportional to the volume. And this is clearly unphysical if you look at the problem from some quantum view. And of course, you can solve this. And there are many solutions. and some of them are mathematically very sophisticated. But a physically natural solution is to add very small external field, infinitesimally small symmetry breaking field. So what you do usually is that instead of this simple Hamiltonian without a magnetic field, you add this term, which is this. This is usual external magnetic field, and define corresponding thermal expectation with H. Then you can prove that if you consider the expectation value of O divided by V in this expectation value, and take the infinite volume limit first, and then let H go to 0, then you precisely get this non-vanishing quantity that is spontaneous magnetization. And of course, the order of limit is very important. If you first take H goes to 0 limit, then you only get 0. So this order is very important. So this is something which is very well known, and I can talk in classes. And so the lesson that we should learn is that Hamiltonian without magnetic field can lead us to an unphysical equilibrium state, which has long-range order, but which has no spontaneous symmetry breaking. But we get physically natural equilibrium states by adding infinitesimally small symmetry breaking field. So this is something we should keep in mind when I go to more content problem. So let me spend some non-trivial time explaining the improvement of Tasaki theories for the ground state of Heisenberg antiferromagnet in higher dimensions. So long-range order and spontaneous symmetry breaking in Heisenberg antiferromagnet. So again, the definitions. And again, lambda is the d-dimensional hypercubic lattice with periodic boundary condition. And now I consider spin system with spin s equal 1/2, 1, and so we put spin on each side. Well, I fix spin, but you can think about spin. Yeah, but anyway, I fix the magnitude of spin and put spin on each side. And this Sx denotes the spin variable at side x. So I'm using x and y to denote the lattice side. So I'm going to use 1, 2, 3 to denote the spin component. But sometimes I would call this Sz. This is usually we call Sx. But this is spin variable, and this square should be equal to this. And the Hamiltonian for the Heisenberg antiferromagnet is this. So again, you sum over nearest neighbor pairs, but now this is antiferromagnet. We don't have minus sign here, so spins want to point in the opposite direction. So we want to examine, and we are interested in the ground state property of this. Okay, in dimensions, I didn't write this, but dimension is greater than equal to 2. And first, this is a fundamental basic theorem concerning this model, which was proved by Marshall, Montano, and the lattice improvement. And it said that the ground state in the whole Hilbert space of this model, for any, this is for finite. For any finite L, the ground state in the whole Hilbert space, which I denote by phi ground state, and is unique and has total spin 0. And this is now it's an easy theorem. You can just apply Perron-Frobenius theorem to this problem, and you will automatically get this. But this is a basic theorem. So the ground state is unique. I also love black here, so let me write. This is the unique ground state. Now, more important and difficult theorem to prove is the existence of long-range order in this ground state. Now we are interested in antiferromagnetic long-range order. So simple total magnetization does not tell us about the order in this case. So we need this strange order parameter, which is sometimes called staggered magnetization. And so I just sum over all the lattice sides, and this is just the alpha component of spin operator. But here I have oscillating sign. And this is plus or minus 1 depending on x is on even sublattice or odd sublattice. But I've drawn this in advance. So in plus and minus 1 oscillates like this. So the neighbor of 1 is minus 1, neighbor of minus 1 is always 1. Okay, so this sort of picks up the order which we expect to be there. So this is the order parameter O. And then this is a very difficult theorem proved by Dyson, Lee, Simon in 1978 and improved by others. And this said that for any S in dimension higher than equal to 3, and in dimension d equal 2 for s greater than equal to 1, the ground state exhibits long-range order, antiferromagnetic long-range order. More precisely, it says that there exists a finite constant theta, which of course depends on s and d, and one has this inequality. So the O alpha squared, expectation value of O alpha squared is greater than this V squared times theta. And of course, since the ground state is unique, this is SU2 invariant, so this is independent of alpha. So this has been proved, and this proof is totally not trivial, and it uses a property called reflection plus 3. Anyway. And so this is proven. This is difficult, but it's known. But now, at the same time, as I said, the ground state is unique. So it is SU2 invariant. So obviously, if you take the expectation value of order parameter in the ground state, it's just vanishes. So as in the Ising model, without magnetic field, the ground state exhibits long-range order, but no spontaneous symmetry breaking. So this is somewhat strange. So this has long-range order, but no spontaneous symmetry breaking. Okay, so this is just what I said. So again, so the ground state satisfies this and this. So this means that this is, I'm repeating what I said in the Ising model. If you look at the variance of O, it's of order V squared. And this means that in this ground state, O alpha has huge fluctuation, and this looks very weird. This looks strange from some other point of view. And the important remark is that this happened in the ground state because we are looking at a model in which the Hamiltonian and the order parameter do not commute with each other. So if you are looking at the ground state of ferromagnetic Heisenberg model, there's nothing strange like this, and everything is just clear. But in many models, order parameter and Hamiltonian do not commute, and especially in field theory, I think in all models, non-trivial models, they do not commute. So that's the point. Okay. So now I want to move on. So I would like to tell you that when you have this strange situation that the ground state exhibits long-range order but no spontaneous symmetry.
So actually, this antiferromagnetic Heisenberg model is just 2D quantum, even for the quantum case. Anderson in the case used this RBB, photonic RBB axis. So that photonic RBB axis, I think, is also have to allow offset factor on the order, but it's the total spin is zero.
Right. Yeah. You can cook up many. Yeah, but yeah.
So just that kind of model.
Well, this is the model. I mean, we still don't know what the ground state exactly is, but we know that there is long-range order. Yeah. By choosing nice RBB, you can cook up a state which is totally singlet, but still has long-range order. But of course, if you do an experiment, you see many. So you don't see this in experiment. Okay, so anyway, first of all, so I want to tell you that when in this situation, the ground state with a long-range order and without SSB, there are several interesting happens, at least theoretically. And one thing is the existence of low-lying states. So I define O plus minus using familiar formula. So O1 plus minus I02. So this is simply this. And by using this lowering and raising operator with this stubborn sign, I define a variational state that I call psi L, and that is I simply hit the ground state, which is highly non-trivial. I don't know what this is, but I hit this phi ground state L times with this O plus and normalize, and this is almost the same thing. And so this one has total S. Fixed total SZ, total S3, which is equal to L. So it's orthogonal to the ground state. And the first theorem by Tasaki states that this has very low excitation energy. It's very close to the ground state. And if you, the difference between the energy expectation value of this guy and the ground state energy is bounded from above by L squared over V. So like for small L, it's proportional to 1 over V. It's very, very small. And so this can be first proven. So this is a low line state. So slide now is I hit the ground state with 0 plus and no minus. And this is a low line state. It has very low. Has very low excitation energy. And given this, it's just an exercise to show that there are energy eigenstates with very, very low energy. So you can prove that there exists an energy eigenstate phi L whose energy is EL and whose total SZ is equal to L, and its excitation energy is bounded from above by L squared over V. So this shows that a weird, strange ground state with long-range order and without SSP inevitably implies the existence of an ever-increasing series of low-line excited states. I say ever-increasing because this holds for L satisfying this. So if your V gets larger and larger, you get more bunch of low-line states like this. And this has been known, especially by those who do numerical exact diagonalization of spin systems. And people started to call this Anderson's tower. And they claim that it's in Anderson's paper, but Anderson's paper, is this on YouTube? Professor Anderson's papers are so deep that it's hard to understand what is really implied there. But I don't know how to, it's hard to find out the exact statement in Anderson's paper, but anyway, this is called Anderson's tower. So anyway, so here is a ground state with long-range order without SSB, but we proved that there are a bunch of low-lying excited states here. And, you know, they are very low. So this is 1 over V, if L is 1. So if you have spin wave excitation, it has very low energy, but the energy is proportional to 1 over L. So this is 1 over L to the V. So it's really, really, really low energy excitation. And, okay, so, but this is low-lying state, but this, of course, exhibits SSB, but still no long-range order, but no SSB. So our goal is to understand SSB like in the Ising model. So what can we do? Well, this is the idea of proof, I'm sorry. This is the idea of the proof about how to show this thing. And the actual proof by Hal Tasaki is really a headache. So let me give much easier thing, which was done by Horschen from the Linden long time ago. And this is our triangle state. We hit phi ground state by this non-Hermitian O plus. But it's not easy to treat. So this guy is treated much easier version where they hit phi ground state by this Hermitian operator. And in this case, this is a very clever trick. And then I'm going to explain everything here. So take this variational state and look at the difference between this guy and the energy ground state energy. So you plug this definition in, you get this. And now from here to here, it's almost trivial. You just put 2 here twice. And this is just twice the ground state energy. Because H is here, this can hit phi ground state to get E. Yes? And this can hit this guy to produce a ground state. So this is just trivial. And now, this is very clever. These guys are clever. If you look at this very, very carefully, this can be rewritten, rearranged as a double commutator. It's commutator O1H and commutator O2H. And so what they got is that this variational excitation energy is precisely written in terms of the double commutator. Now you recall that this O1 and H are both local operators, sum of local operators. Then the commutator itself is also the sum of local operators, and this O1, this is order V, this is order V, but this commutator is order V, again, not order V squared. And again, take commutator, it's again order V. So you see that the norm of this double commutator is order V, bounded by order V. And so this takes care of this upper stair. And as for this downstairs, we know that this guy exhibits long-range order in this case. So by using this and this here, you find that this variational energy is of order 1 over b. So this is the simplest part, and but of course the main result by Tasaki is the existence of a whole bunch of power, and the proof is really, really painful. And I found a less painful proof recently, but it's still painful, and I still have to write this down. But anyway, it's been proved. Okay, so now this is what I said. Okay, so now we started from this ground state with long-range order without SSB and constructed a bunch of low-lying states. But still, it doesn't exhibit spontaneous symmetry breaking. How should we go? How should we proceed? Well, the next thing we do is to sum all these low-lying states up like this. So the third state is sum of these low-lying states from minus k to k, and I just normalized it. And yes.
Did you choose this order problem?
Oh yeah, I will, because I want it. And I would argue that this exhibits spontaneous symmetry breaking, the full spontaneous symmetry breaking. And in order to do that, I have to define order parameter. And this is my definition of order parameter. And this is a bit not easy to understand. But you know, here I have 2n, all to the power 2n, and expectation n all to the 1 over 2n, power 1 over 2n. So this is, and I take n close to infinity. So this is like infinity norm, usually. So you get the maximum. But this is not a simple maximum. Here I insert infinite polynomial. So this is a kind of max norm in the infinite polynomial state. And this you can, well, you will, after some time you can convince that this really picks up the maximum possible order happening in this ground state. And also we can show that this m star is greater than or equal to 3 times square root 3 times theta. This 3 comes from SU2, but anyway, this is too much. But anyway, we can show this. This is not trivial condition. So anyway, we have a reasonable definition of m star, that is the order parameter. Then what we can prove, actually what I could prove recently about this psi k is this. The inequality version of this one was in old Tasaki, but all these are new. And what I could show here is that I first look at the expectation value of O1 divided by V in the infinite value. But again, the order is important. I first let V goes to infinity, and then let K goes to infinity, using this state. And then I say that I get this maximum possible value for the length of O1. So this tells you that in this limit for large V and for large K, this psi has the largest possible order with respect to measured by O1 divided by V. And also, this is supported by this result for the expectation value of O1 squared. And now I show that again in the same limit, this O1 squared divided by V squared is equal to m star squared. This means that this guy showed no fluctuation. And for other components, it's 0. So this means that, in short, this means that in the low-lying state psi k, the order operators, this guy, shows very small fluctuation and essentially behaves like a classical quantity, as people do in mean field calculation. So this becomes something like a classical quantity, and this shows that this one divided by, normalized by V, almost behaves as a classical vector with component m star 0, 0. So
motivation. So usually, if I try to pin down like I
will come.
So they
Yeah,
will.
yeah, that will come next. So this
This is the same. It will be same, right?
oh, yeah, almost the same. Yeah, but actually, we cannot get. Okay, I will tell you. But yeah, actually. So, but of course that will be the story. So I want to go to SSP. So now, now this is again low line state. But simply this is construction, right? And that whole thing. I simply constructed, but this has long range order in both SSP. So with this state, I will proceed.
Do you have any restriction for O operator?
What?
Do you have any restrictions for O operator?
What intuition?
Restriction.
I'm sorry. What's
Restriction.
Oh, restriction. Oh, no. This
How
is,
do you pick up the
yeah, this is very specific. O1 is already defined. So O1 is simply this. This is the first. This is just the sum of all the spin variables, spin operators, with the status. Oh, so it's the same thing. So okay, O alpha.
Okay.
1, 2, 3. So this is SU2 or SO3 problem. So this is an order problem for SO3. Okay, can I go on? And again, so this is not a fashionable talk, so I have some idea of the proof part. So why does this work? So I said that it's already there. So I define this state, which is the sum of all these low-lying